Hello, I am McElory Hoffmann, CEO of Praelexis. In this presentation, I will discuss our credit modeling tools. It offers a streamlined and integrated solution for the end-to-end credit modeling process. Before I discuss our approach, let us look at the usual way of work. Credit risk management often involves the cooperation of many different teams and stakeholders within an organization, the use of a large number of different software tools across teams and within teams, model development by one team and deployment by another. This is typically risk prone and things may get lost in translation. Largely manual model validation and review procedures. And then finally, a difficult and manual model monitoring procedure. The usual way of work leads to several problems. Some of these problems often faced with the usual ways of work are: there is a difficulty of streamlining communication and processes between teams. Another problem is that very little or no integration exists between software tools. Many times the output of one tool is manually fed into the next. This is time consuming and error prone. Yet another challenge is the difficulty of rebuilding models to make them suitable for deployment. Moreover, long model development and approval cycles lead to long lead times for new models. Once the model is in production, the problems are not disappearing. Typically, model monitoring is this time consuming that leads to a negation of model monitoring altogether. The net effect is that models may take months, sometimes years, before they are ready for productions. Long development cycles run the risk of models already being outdated by the time they are production ready. COVID-19 is an extreme example. As we observe these problems in industry, we developed a single unified framework for the credit development and management process. Our approach is based on several common open source tools within the data science world, such as Jupyter Notebooks, Spark, Python, Scikit-learn, TensorFlow, and standard version control. Our solution works on premise and in the cloud. We recommend, however, a cloud-based approach. The following principles guide our design. It should be easy to load data, pre-process, and explore it using the standard tools. It should allow for fast model iteration and experimentation. Business processes, such as the approval process, must be integrated directly into the system. This allows for more control and better management. A good analogy is making a car faster. You can make it faster by building a faster engine or better brakes. We believe that the controls around the credit process is the brakes of the system, which will ultimately lead to an overall faster process. The solution must allow model performance stability insights. This helps with effective validation of the models. Deployment should be seamless, but as mentioned earlier, also controlled. Live monitoring of models should take place. It should be easy to integrate between different models, for example, between the probability of default model and the pricing model. This slide gives an overview of the components of the system. The notebook is the master model where the user interacts with the system. It will typically access the Python models in the core credit library, and that's available in the Git repository. From the notebook, the user can develop a credit model, manage the model, and deploy to production. Where necessary, other user interfaces are available. The architecture behind the solution is based on containers. We use Kubernetes as the orchestration system. Once a model is developed, it will be deployed as a container in Kubernetes with its own APIs. Data is typically available in a data lake and many times in operational data storage, providing fast access to data in production. In the sandbox environment, development takes place. As mentioned previously, this is based on Jupyter Labs. Once models are developed, they are deployed in the production environment. Consumers communicate with models through a REST API. Next, I want to discuss the necessary features of credit modeling. Before I do that, I want to remind you of the credit model building process. Typically, a scorecard is built to model the probability that a client might default. A scorecard building process begins with the data, followed by variable selection, dataset partitioning and auto-binning, variable reduction, binning adjustments, and then typically a logistic regression based on the weights of evidence. It is important to note at this point that credit models must be interpretable. Hence, the type of machine learning that can be used is sometimes limited, unless a model useful interpretation of the model is available. A scorecard gives the risk that the client will default. In other words, the risk that the client cannot repay a loan. The affordability model tells us how much a client can afford to pay back. Remember, responsible credit is always important. Combining the affordability with the probability of default allows one to make an offer. An offer is the loan amount, term, and the interest rate. And of course, these models must be available in a production environment and must many times be able to function in real time. Now I want to go through the necessary features for a credit modeling framework, platform or tool, the way you want to call it. And these are also the things that we have implemented. On this slide is a summary of all the necessary features for credit modeling. In addition to the supporting tools and infrastructures that is required to manage credit models, model building tools are of course very important. Building credit scorecards involves a series of well-established steps that involves, amongst others, the determination of the definition of bad. In other words, what is the probability of recovery if a loan is in arrears? This is determined using roll rate and vintage analysis. Weights of evidence is a nonlinear transformation that renders the model more robust. This requires manual adjustment of bin boundaries. Thousands of variables are typically available. Those with the most predictive power should be selected. It is therefore critical to have access to efficient and robust implementations of the required tools and methods. Next, I will show in a bit more detail how we implemented these methods. In order to establish how likely it is that a loan can recover from being in arrears, the migration to the different delinquency states, for example, 0 days, 1 to 30 days, and so forth, over time is monitored. Performing this analysis can give insight into when a client is unlikely to recover from falling behind. These insights can then be used to inform the effective definition of bad loan. That is, loans that will unlikely recover. Let us look in a bit more detail. In the example shown there, all loans, and the typical case starts with a 0 delinquency. First, a time period is specified for the maturation of the loans, for example, 12 months in the table. At the end of this period, the delinquencies of the loans are recorded. A second period, again 12 months above, is specified and the delinquencies after this period is recorded. For example, of all the loans that had a 0 delinquency after the first maturation period, 83.88% was still at 0 delinquency. 11.93% migrated to 1 to 3 days delinquencies, and so forth. The last 3 columns summarize how the loans migrated. Backward means the percentages that improved. Middle means the percentages that remain in the same status. Forward means the percentage that move to the worst category. In this slide, we see another visualization as available in our credit modeling tools. Uh, and this is a visualization of the roll rates. Variable selection is another important step in building credit models and allows modelers to reduce the number of variables and models while maintaining performance, leading to interpretable and stable models. Above two criteria are shown. Information value, that is how well a variable separates good from bad, and then the popular Gini index, and that is the predictive power of the variable. A model is trained using the variable and used to make predictions, and then you get to the Gini index. Weights of evidence transformations allow modelers to bin data efficiently. Weights of evidence transformations are a nonlinear transformation aimed at extracting optimal predictive information from the raw variables and typically involves one, binning the variables, and then two, transforming them to weights of evidence rules. This is a key step in credit modeling and, if performed correctly, can increase model performance significantly. There is a complicated nonlinear interaction between weights of evidence and bins, and it is important to get it right. Finding optimal bins is still a manual process, and we provide a convenient tool to help with this. Here is a short video clip demonstrating the weights of evidence transformations. As you can see, we allow some interactivity within the notebooks. The previous variable selection step selected variables based on their individual properties. Now we investigate how the variables work together to determine the final model. For examples, variables with high correlations are redundant and should be removed. This graph shows how the variables are grouped into correlated clusters. The most representative variable is selected from each cluster to go into the final model. It is important to emphasize that the modeling process is iterative. This means that the model is not yet done and invariably goes back to test hypotheses, experiment with different selections of variables, and so forth. Once the model has been trained, it is of course very important to ensure that the model performs well. This can be done by simply plotting and evaluating the receiver operating curve in order to evaluate the true positive and the false positive rate of the model. This should of course be done on additional held out data sets. In this slide, we can see that the example model has relatively high performance and that the performance is stable across the different data sets. After a scorecard model has been trained and evaluated, we can also gain insights into the model by inspecting the model summary. This gives us an idea of how the different variables influence the final model output, in other words, the credit score. Being able to visualize such a model summary can therefore serve as an important tool in a final inspection of the model and can assist in identifying aspects of the model that might be incorrect. Once a model has been developed and thoroughly validated, it can be deployed to the appropriate environment on the available compute resources. Credit teams often struggle with this part of the process. It can be complex and requires a very different skill set than the modeling process. Even when credit teams have DevOps teams that assist with the deployment phase, communication between the teams and the frequent need for redeveloping can lead to significant inefficiencies. It's also error prone. It is therefore extremely advantageous to have access to tools that streamline this process and allow the developed models to be deployed seamlessly. Deploying poor performing models or incorrect model versions can, however, be catastrophic and is therefore equally important to have effective control over the deployment process. with the responsible individuals validating and approving model deployments. Remember about my example that I mentioned earlier of the car that we want to build faster, either by making the engine faster or having better brakes. Once a model is deployed, it should be continuously monitored in order to ensure that it remains stable. Environmental changes, of which COVID-19 is an extreme example, should be detected early. If not, the model might become obsolete and invalid. It is therefore essential that deployed models are continuously and automatically monitored to ensure that any deviation in performance is identified immediately to ultimately prevent loss of revenue. Again, on the slide is an example of such a model and population stability check as done in the tools that we developed. At Praelexis, we try to continuously improve the credit modeling process. One such an example is continuous weights of evidence transformations. As mentioned earlier, there is a complicated, non-linear relationship between the bins and weights of evidence. The optimal relationship is determined manually and therefore suboptimal. Continuous weights of evidence is a way to estimate the nonlinear weights of evidence transformations without discretizing a variable. This avoids creating discontinuities in the variables, which could result in similar individuals obtaining significantly different credit scores. It also reduces the need for manual building by using an algorithm to determine the optimal weights of evidence transformation. I have discussed in this presentation our tools and methodologies for credit modeling. As mentioned, working with many disparate systems can be inefficient and error-prone. Therefore, access to proper modeling tools is crucial. Having the ability to deploy models quickly and reliably is equally important. Continuous model monitoring will prevent loss of revenue. The established methods have been used successfully for many years, but that does not mean that there is not room for improvement. Many thanks for attending my virtual talk. You are welcome to join me in the speaker lounge if you have additional questions.